Hello everyone. We are group 13 here to present the paper MemcachedGPU Scaling Up, Scale Out Key Value Stores. Authors of this paper are Taylor H. Hetherington, Mike O'Connor, Tor M. Amdot. This paper is presented by Arpita Vasudeva and Minru Shen. The main motivation for this paper is that the data centers contain large number of servers, memory, network hardware, non-volatile storage, and cooling that together can consume tens of megawatts of power. Demand for higher performance in data center is terminally increasing. The focus on specialized hardware accelerators such as application specific integrated chips and FPGAs to improve the performance of individual servers. ASICs can provide higher efficiency than reprogrammable FPGAs. Generality is important in the data center to support many constantly changing applications. But FPGAs can provide high levels of efficiency for single applications. However, long reconfiguration times on current FPGAs may mitigate some of these benefits if the full application does not fit on FPGAs. Hence, we cannot trade off easily performance for power. So, to have a perfect data center, the ideal requirements are we should have high energy efficiency, high throughput, and performance. Providing all of these at low cost, low programmability, and low latency. Before we can understand why we used Memcache GPUs in this genome software, we need to understand what is Memcached. So, Memcached is a general purpose scale out in memory caching system used in distributed database systems to improve performance by reducing the amount of traffic backend device databases. Memcached provides a simple key value store interface to modify and retrieve data from the hash table. The key value pair and corresponding metadata is referred to as an item. To avoid expensive memory allocations for every write request, Memcached uses a custom memory allocator from pre-allocated memory slabs to store this item. To reduce memory fragmentation, Memcached allocates multiple memory slabs with different fixed size entries. The hash table stores pointers to the items stored in the memory slabs. Keys are hashed to look up item pointers from hash table. We are using NIC in our genome software. It is always good to understand what is NIC. NIC is nothing but network interface architecture. So, the NIC connects host CPU via PCI bus. Network packets enter the receive queues, nothing but the RX queues at the NIC, which are copied to pre-allocated DMAable RX ring buffers, typically in the CPU memory. The NIC sends interrupts to the CPU for one or more pending RX packets. The NIC driver copies packets to Linux socket buffers (SKBs) and return the RX buffer back to NIC. Optimization such as direct NIC access, that is nothing but DNA, may be reduced may reduce memory copies by allowing applications to directly access the RX buffer. Next, what is GPU? What is GPU architecture? GPU is nothing but graphical processing units. These are throughput oriented offload accelerators traditionally designed for graphics. Recent GPUs are capable of running non graphic applications written in CUDA or OpenCL. These are C like languages. CUDA applications are composed of two parts: a host side CPU, which is responsible for initializing GPU's environment and communicating with the GPU, and a device side, which executes one or more kernels. A CUDA kernel is a user defined parallel section of code that runs on the GPU. Scalar CUDA threads are grouped into wraps typically containing 32 threads. Each thread in a wrap executes instructions in a lockstep single instruction multiple thread fashion. Wraps are further grouped into cooperative thread arrays. This is nothing but CTAs. The host communicates with the GPU through a set of hardware managed CUDA streams, allowing for concurrently operating asynchronous tasks, example, computing or some data transfers. Next, the main idea of our paper. What is Genome? Genome is nothing but GPU Network Offload Manager. Genome, using Genome, we achieve high throughput, low latency, and energy efficient UDP network processing on commodity Ethernet and GPU hardware. We use GPUs because they are flexible, energy efficient accelerators for general network service in data center. We exploit request level parallelism through request batching on massively parallel GPU architectures. Request batching in Genome is done per request type to reduce control flow divergence among GPU threads. Smaller batches size minimize batching latency. However, increases the GPU launch overhead and low GPU resource utilization, which reduces the throughput. So, at this point, if the latency is increased, the overhead on the GPU kernel will also increase. Therefore, we find an optimum point of um, combining 512 requests per batch, and we understand that 512 requests per batch provides a good balance and throughput and latency. Genome software architecture. So basically, genome contains two parts: genome host, which is responsible for interaction with NIC and the pre post GPU data, and task management. Genome device, this is responsible for UDP packet processing and application processing. In the next slide, we understand the interactions between NIC, CPU, and GPU in genome along with CUDA kernel for genome dev can be seen. So here what is happening is, here we can see the RX packets. These are directly DMA'd into the GPU's global memory. This is genome dev. The expanded form of genome dev is given here. Genome dev consists of a global memory, shared memory, a buffer which has, a place where we load the receive packets and where we store the transmit packets, and UDP processing component. So this is the expanded form of genome dev. A genome host consists of an OS, user level, and memcached item values. So the basically the RX packets are directly DMA'd into the GPU's global memory. Only metadata describing the request batch is sent to the CPU. We focus on accelerating the RX path in genome, while genome can implement a similar transmit path using GPU Direct. MemcachedGPU uses a third-party CPU Linux network-based bypass system, PF ring, to accelerate the TX path on the CPU. Next, let us understand what is the proper functionality of genome host. Genome host is composed of three software components: modified Intel IXGBE network driver, Genome ND, and Genome KM. Genome ND is nothing but a network driver, and Genome kernel is, KM is nothing but kernel module, and also a genome user. Genome ND DMA's RX packets directly from the NIC to the GRXBs in GPU memory using GPU Direct and constructs metadata in CPU memory describing the batch of GPU packets. Genome ND also passes the batch metadata to Genome KM once a batch is fully populated and ready for processing. The NIC populates the GRXBs in order they were registered. The function of Genome KM is that it acts as an interface between the Linux kernel and the genome user. It looks for genome user to communicate indirectly with the NIC, such as configuring the NIC for use of genome, reading metadata for request batches, and recycling GXBs. Genome user. Genome user consists of pre-processing and post-processing user level p-threads. Genome pre retrieves request batch metadata from genome KM, performs application specific memory copies to the GPU, launches CUDA threads that performs network service processing on the batch of requests and constructs CUDA events to detect when the GPU processing completes. Genome post polls the CUDA events waiting for the GPU network service processing to complete, populates the response packets with the application specific data, and transmits the response packets using PF ring. Now, we also have another component called as non-GPU direct. This is currently the only supported on high performance NVIDIA Tesla Quadro GPS to evaluate Memcache GPU on lower power and lower cost GPUs. What is Genome Dev? Genome Dev leverages additional helper threads to perform parallel tasks related to single network requests, exploiting both packet level and task level parallelism to improve response latency. Genome Dev groups wraps into main and helper threads. Main wraps perform network service processing, while helper wraps perform UDP processing and response packet header construction. The main helper wraps also cooperatively load Rx data and Tx data between the shared and global memory efficiently through coalesced memory accesses. Now, what is Memcache GPU? Here we can see that we have GPU memory and CPU memory. GPU memory is mainly used to for all the GET requests. GET requests is nothing but retrieval of the data that is already present in the memory. And the green part is shown like it depicts the GET requests. CPU memory is used for set requests. Set requests is mostly for new data insertion or updating the new already present data or deleting any data from the memory. So the blue part represents the set requests or the data that is stored in the CPU memory. Memcached and data structures. Get requests. Memcache GPU performs the main GET request operations on the GPU. This includes parsing GET request, extracting the key, hashing the key, and accessing the hash table to retrieve the item pointer. Aside from the item values, all of the Memcache data structures accessed by GET requests are stored in GPU global memory. Each GET request is handled by a separate GPU thread, resulting in memory divergence on almost every hash table access. However, the small number of active GPU threads and GPU's high degree of memory parallelism mitigates the impact on performance. Set requests. Set requests require special attention to ensure consistency between CPU and GPU datasets. Set requests follow the standard memcached flow over the TCP through Linux network stack and memcached code on the CPU. They update the GPU hash table by launching a naive set request handler on the GPU. Set requests first allocate the item in memcached memory slabs in CPU memory and then update the GPU hash table. This ordering ensures the subsequent GET requests are guaranteed to find a valid CPU item in the GPU hash table. Set requests update the GPU table entries, introducing a race condition between the gets and other sets. We have described a GPU locking mechanism to ensure exclusive access for set requests. This is explained in the next part.
Thank you, thank you, Appreciate. I'm Ming Chen. Now I will introduce the hash tables. For uh, firstly, before we need to understanding the GMEM uh, memory cache hash tables, we need to understand the baseline memory cache hash tables. The baseline memory cache hash table is dynamically sized with the hash chaining on collisions. What is the hash chaining? You can see the below graph. The yellow part is for one data, and the red part is for another data. When the yellow data is increased, and he will automatically allocate to the next block of this current block. When the next block was occupied by the red data, and the collisions happens. And to deal with these collisions, the hash chain will link to the next available block to uh, increase this available space for the yellow data. And this profit for the GPUs for two main reasons. First, to reallocate the space for the current data will degrade the performance. And second, that degrade the SIDM efficiency to search an element. Because this size of the data is unknown, you need to search one by one to get the matched data. And if we use another solution, maybe it can solve this problem. Here's the another solutions. We use a fixed site storage structures such as n-ways set associative. For the n-ways set associated, we can see these two diagrams. For the left part is direct mapping and cache fields. We can see it in the cache memory. It stores the link of the store the index of the main memory, and each block stored the index. And the two-way associative cache field, we store the index in one block with many index from the main memory. N-way set associative. The n means the index numbers in this set, which means a set with n-weight associative means the set contains n cache lines, and the next cache line has n gaps from the current cache lines. If you want to look at the more details, you can click the link below. The hopscotch hashing. The traditional hopscotch hashing is the way to solve the collisions problems. As we previously mentioned, the n-way set associative Each cache line has an n gap from the current cache line. And uh, if we apply the traditional hopscotch hashing, uh, for example, we need to add 6 to the block 6, add x to the location 6, while location 6 was, was occupied by 8, and A needs to hop to the another block. In this example, the N is 2, A is hop to the C, and C need to hop to the D. But the position 11 is occupied by D. D needs to hop to. Then he look the other block 13th, and this block is empty. So there's a reallocate D to the 13th and B to the D positions and A to the C's positions. And then the position 6 is available now. Then we add X to the location 6. This has problems because when you reallocating this hope, they will take the actual time consuming or the calculating abilities. And what is the MemcachedGPU hash table solution? First, it implements a fixed size set of sensitive hash tables. In this paper, they applied 6-way set size, which means 16 cache lines consist a set. And it also has a modified version of hopscotch hashing. In the traditional ways, we just mentioned it reallocate, but in these solutions for the memory cache GPU, they did not reallocate any elements. They used the evasion to evade and occupied element based by the last recently used LRUs. And each table, hash table inches contains a header and a physical things. And the headers contains a valid flag, a last access timestamp, the length of the key and the values, the pointer of the item in the CPU memory, and optimizations from that includes a small 8-bit hash key of every header. Why it has 8-bit hash key? Because to traveling this hash table set, first to compare the 8-bit hash, it will reduce the cost to compare all full keys of every inches. First compare the small key. When the small key is matched, then check the full key to identify which element is required. And this slide explains why these solutions apply the 16-way set associative. As we previously mentioned, the hash chainings have two disadvantages for the search and allocate the incoming data. But you can see the 32 ways has better performance than the 16 ways. Why we apply the 16 ways? That's because in a set of the cache lines, you need to check all the index in that set. If the set size is too big, that will increasing the worst case number, meaning you need to travel to 32 index to get the memory address. And for the 16 ways, it has about almost the same performance to the 32 ways, but it reduced the worst case number of engine search on and access to the hash tables. And let's talk about the hash table collisions and the evictions. For the baseline memory crash, to avoid the eviction and implement the base ideas is using the global lock and protect the access the global less recently used queues for managed item evictions. And it would require the serializing all the GPU threads for every memory crash request. But for the memory crash GPUs, they manage local less recently used per hash table set, such as that get and set requests only need to update the timestamp of the hash table entries, which means the memory crash GPU has more flexible than the baseline memory crash. And let's talk about the storage limitations. Here's an example for the high-end NVIDIA Tesla K40 seat, which has 12 gigabytes GPU memory. To implement these solutions, it will consume 240 megabyte GPU memory for the data structures such as GPU receive buffers, response buffers, and set request buffers. And it also remained 11.75 gigabytes for GPU hash table and the lock tables. And then let's talk about the GPU current controls. They have two main type requests. First, gaps request. It did not modify the hash table entries. It just update the timestamp. The second type is set request. It requires to exclusive accept things then modifies the entry. Set request also modifies the data in the main memory. For the memory crash GPUs, to handle this two type of requests, they employ a multiple readers, and each reader is shared, and one single writer is exclusive. That protects the data safety because the read activity did not modify the real data in the memory, so it just needs to update the timestamp for the last recently used timestamp. And for the data safety, they applied a single writer, which is implemented by the CUDA automatic compare and exchange that protect the data safety. And the exclusive lock ensures the exclusive access for the set request to modify a hash table entry. Let's talk about the race conditions on eviction. When the memories process the multi-thread in parallel, and it needs to compare the timestamp. That's why we call the race condition. If the set needs to evict M items, it records the last access time stamps for the to be edited items. And then after updating the GPU hash table, the set pulls all GMO post GCTs and starts until they are all greater than the eviction timestamp before the evicting the items. That ensures the alt get period to the set has been complete before the get request retrieve the data from the main memory. Now, let's talk about the evaluations for these solutions. Here's the server and client configurations and the GPU evaluations. Um, to evaluate the performance of the solutions, they use the three type graphic cards. And we can see the GTX 750 Ti have the lowest TDP, which means the power consumed is the lowest, and the cost is also the lowest. Here's the evaluations about the MemcachedGPU's performance. We just focus these two columns, KRPS per watt and KRPS per dollars. These values are the higher values represent the better performance. We can see it. The values of the MemcachedGPU have the average performance is the best compared with the other solutions. Conclusions. GMO is a GPU's accelerated networking framework which enables high throughput network centric applications to exploit massive parallelized GPU to execute both network package processing and application code for an offline limit study and highlights that the MemcachedGPU may be able to scale up to 2 times than the throughput and 1.5 times greater the energy efficiencies on the low-powered NVIDIA Maxwell GPU. That's all. Thank you.